everyone, and welcome to today's Stu Talk. Today we have Kasun, who is a PhD student in engineering, and he's just handed in his thesis and waiting for his viva. So Kasun his work involves the development of a new vibration-based approach for monitoring bridge scores. And today he'll be speaking to us on the topic, monitoring the health of bridge structures. So carry on, Kasun.
Yeah, thank you. So guys, I'm going to talk to you today about monitoring the health of bridge structures. So when you think of health monitoring, I'm sure the first thing that comes to your mind is the health of humans. Human health has advanced so much. We know that when we don't think about the human health, if you think about the heartbeat, it's so easy. We can look at the heartbeat and say how healthy the person is. Similarly, we can look at the health of the structures. When it comes to the health of the structures, we can look at the bridges also have vibrations. Do you know why the bridges have vibrations? Any suggestions?
Would that be to enable them cope with pressure?
Exactly. So vehicles going over the bridge, wind hitting the bridge, water hitting the bridge. So because of all these causes, we have different types of vibrations on the bridge. And these vibrations can be used potentially as a way to measure the different vibration-based properties. So the idea is that normally these vibration-based properties do not change under normal circumstances. But whenever there is a damage, we can expect that these vibration-based properties do change. And so if you look at this bridge, so you can see that really small types of vibrations are present in this bridge, right? So these vibrations are present because of the wind. So this is an exceptional circumstance. So normal bridges do not have these types of exceptional types of vibrations. But what normal bridges have is really, really small vibrations. If we have really good accelerometers, we can place these accelerometers on the bridge and we can measure these vibrations. So the reason for these types of vibrations to occur is because there is input vibration coming, input excitations, different types of excitations coming from wind and different types of excitation sources. And these vibrations provide a very wide band. That means wide band means it is across a very wide frequency range. Every bridge has its own natural frequency. Actually, there are multiple natural frequencies. And these, whenever the input excitation is actually exactly at that input excitation, natural frequency of the bridge, what happens is there's something called resonance. I have to distinguish between resonance and general vibrations. Resonance is a really bad concept for bridges because resonance means the bridge can vibrate so much. And I'm sure maybe you have seen a bridge failure called Tacoma Narrows bridge failure. So whenever there is resonance, there can be so much vibration and it can actually fail. But when there is really small vibration, like I told you before, when there is all the wide bands of vibrations occurring, there is energy concentrated nearby the natural frequency. But by looking at that, we can say where the natural frequency is. So resonance is a very different concept to normal vibrations. So we are looking at normal vibrations. So the reason for doing all of these is because to avoid these kind of bridge failures from happening. So as you can see here, the bridge here, this is a very high profile bridge failure. And this bridge failed because of something called scour. And this is what I have been studying for my PhD. And this bridge failure happens because of the removal of soil around the bridge foundation because of the rapid water flow. So especially during flooding, when you have fast water flow, you can imagine the water coming in and hitting this column, and this column is blocking all the water flow, and there's going to be turbulent water. So turbulent water is really fast, and this water can wash away some of this material. And you can see that it creates these kind of scour holes. So it's like a pit, and you can imagine that the bridge is fully supported by the soil. So if the soil support is removed, we can expect the bridge is going to be unstable. and it can even lead to bridge failure. So this is quite significant, and the significance, you can see this shows 500 bridge failures in the US from 1989 to 2000. You can see that there are out of large number of bridge failure causes. So there are large number of causes which a bridge can fail. For example, steel and fatigue can fail a bridge. Ice, fire, earthquakes, deterioration, overloading, collision, scour and flooding. Although there are a large number of bridge failure causes, only one failure cause stands out. That's called scour and flooding. So this is what I have been focusing on. So the first slide I showed you about vibration. So second slide I showed you about scour. So what I did is that I'm trying to use the vibration of bridges to monitor this damage cause called scour. So this is called vibration-based scour monitoring. So with this technique, what simply happens is that we place accelerometers on a bridge and we measure different properties such as the natural frequency and other dynamic parameters. And the idea is that whenever there is scour, because the ground level changes, so you can see the ground, scour means the ground level change, like this previous slide I showed you. So because the ground level change, we can expect these different parameters to be changed. And looking at these parameters, just by looking at these parameters, we can say the scour has changed. So we engineers, we generally like to look at very complex concepts in the most simple form. So if we simplify the bridge as the most simple to the most simple form, that is the lump mass system. So if we assume the ground level to provide a fully fixed condition, so it's really fixed condition, and if we assume all the mass is lumped at the top, we can get the natural frequencies given by this equation. So natural frequency is given by this equation where the EI is flexural rigidity, and without going into detail, so EI, M, and all these other parameters are constant. So only the height is changing under scour conditions. That means with scour, what happens is the exposed height, this height is changing. So with the height change, so scour increases the exposed height, and with that, we can expect that we can see the significant relationship with natural frequency and exposed height. So we wanted to apply this in real life. The problem is that if we try to apply this in real life, we want to first verify whether this technique works in real life. Verifying this in real life is such a difficult thing, because if we were to place accelerometers on a bridge and wait for the bridge to scour for a long period of time, we might have to wait for years and years, but we might not get enough scour. But so some of the researchers who previously attempted to verify this technique actually failed because they couldn't find enough scour that changes in natural frequencies by sufficient amount. So we decided to take a different approach where we went to this bridge. This bridge was very unique because this bridge had scour already. This is a road bridge, and this South Bridge Pier had scour already. I'll show you the scour profile in a bit. So this South Bridge Pier had scour, and what we did was that rather than looking at from before scour to after scour, we went in the reverse way. So we went to this bridge which has scour already, and we measured from reverse. So from scour profile to unscoured profile. So we placed these different accelerometers on the bridge, and unfortunately, 2 of the accelerometers did not work. But what happened was that, so before the scour repair started, we went to the bridge and we took riverbed scans. And so this is showing the side view. So looking from this side view. So this is the North Bridge Pier, this is the South Bridge Pier. You can see that the level before the repair is shown here. So before the repair started, this is the bed profile. And after the repair finished, this is the bed profile. You can see, so you can see the bed profile has increased. So from blue line to yellow line, the bed profile has increased quite significantly near the South Bridge Pier. So this is what we monitored. So before looking at this profile, we created a finite element model. So in civil engineering, we use finite element models. So with finite element modeling, what we do is that we try to model the bridge, different elements of the bridge using very finite elements, and we provide properties to stiffness properties to these elements. And using this finite element model, so I found that these are the different expectations we can have. So scour depth is in the x-axis and the change in natural frequency in the y-axis. You can see that for different levels of scour depth, the natural frequency changes by this amount. So I've assumed two types of scour, so I have to explain that. So local scour is whenever you have scour constrained only to one bridge pier. So if the scour profile is like this, only near that bridge pier, it's called local scour. If the scour profile is like this, where scour everywhere is the same, that's called global scour. So the finite element model showed that local scour would have this blue line, like what's shown in blue line, that sort of variation, and global scour would show what's shown in this orange line. So you can see that for about 3 meters of scour, we can expect about 20% change in natural. This is quite significant because natural frequencies do not change because of other causes, do not change this much. But the problem is that in this real bridge, the scour depth was only 1.8 meters. So unfortunately, experimentally, we could not see this change, expected natural frequency change. So we were actually initially very discouraged and we thought, oh, the whole experiment, everything is gone and it's really discouraging. And then I started analyzing the different parameters. And luckily what happened was that I found some of the new parameters which others have not really looked at. And these parameters actually showed that the scour depth has changed. So it actually became something good. So we found that the mode shape, so each and every natural frequency has a certain mode shape. So you can think of it as a way it dances. So the bridge would like to vibrate at for example, the second mode shape. This is around 18 hertz. So at 18 hertz, it would like to vibrate in this mode shape. So this mode shape is very constant under normal circumstance. But so this is showing before the repair started. So after the repair started, look how it changes. So after the repair started, after the repair finished, you can see that what's shown in the red line. So what's shown in this magnified view, you can see that the modal amplitude has reduced near this bridge pier. So this, what's in the right side. So what's in the right side is actually, if you can remember, that's the south bridge pier. So if you can remember, south bridge pier was exactly where the ground refilling, backfilling occurred. So exactly at the location where the ground backfilling occurred, we have seen a local change in modal amplitude increase. This is quite significant finding because this means that just by looking at the change in mode shape, we can say where the scour is located. So that means we can actually localize where the scour is located. So this is very useful for bridge engineers when they have to implement countermeasures against scour. We can go to the bridges and we can look at we can look at just the mode shape change and we can say, okay, this is where the scour is located. The second another parameter that I found, which others have not looked at in the past, was modal spectral density. So modal spectral density is actually something we can find because in the process of finding natural frequency, it's just a byproduct actually. So this byproduct actually showed that when I used the mean value, I found that over the whole 6 months period from August when we started backfilling scour to November when we stopped backfilling scour, this modal spectral density value gradually reduced. So it's exactly matching the process of which we backfill scour. So this means that if the bridge were to scour, we might see the reverse effect. That means we might see the mean spectral density going up. So these two parameters we actually found shows that the scour can actually be measured by using the vibration. What we did was that we did small scale modeling. So we considered a large bridge and we used a small scale model. And looking at this small scale model, we wanted to do experiments with this small scale model. So whenever we scale down soil, what happens is that scaling down soil involves inaccuracies in stiffness scaling. So because inaccuracies in stiffness scaling is involved, we wanted to always carry out this in a centrifuge. So centrifuge is a large beam. Actually, it's about 10 meters in diameter, and at the end of this beam, we can have this centrifuge package. So this is my centrifuge package. So looking from the top, so this centrifuge package was tested while spinning. So you can imagine it spinning at like 100 times a minute, really, really fast. And during that, during its spinning, we did all the experiments. So it was really exciting because all the experiments were done while it's spinning. So we wanted to have all the mechanical instruments, everything, sensing, everything running under huge amount of acceleration. So I had 4 different bridge models. So one of the bridge models had the full bridge. So you can see model 1 had the full bridge, and the model 2, model 2, 3, and model 4 are just foundation models. So so if you zoom in, this is one of the models. You can see this model 1. So at the top of the model, you can see there's an actuator. So actuator is exciting, providing like impact vibration, and that impact is transferred to the bridge. And then from the bridge model has different accelerometers, and these accelerometers measure the vibration. And after doing one test, we stop the test, and we remove soil, create a scour hole as shown here, and then do another test. So each time we get a natural frequency and mode shape and all the parameter measurement, and we do another test, like that. So I have a video of excitation during one of the models. So you can see this during one test. So what happens is here I have a air hammer here. So air hammer is providing air from one side, and this air is transferred to this hammer, and then from there is this hanging kicker, and then kicker goes and kicks the model, and then creates a vibration. And we have this really small accelerometers, and these accelerometers measure all the vibrations. So by looking at all that, what we obtained was these different natural frequencies. So these are different natural frequencies for different scour shapes. So you can see at the bottom, I've shown different shapes of scour holes. So you can see no scour and local scour only at the bridge pier, and a local scour only at the bridge left abutment, and local scour only at the right abutment, and then global scour. So you can see that every advancing scour step, so what's shown in dashed line shows that for every advancing scour step, the natural frequency has reduced. This is the critical thing. So that means just by looking at the natural frequency change, we can estimate that natural frequency has, that means scour depth has also changed. Another important finding is that we created a numerical model, and the numerical model findings match quite well with the experiment results. So that means using the numerical model in a field scale, we can actually look at the change in natural frequency, and then we can derive, okay, so this is the scour depth that should have happened in this bridge. So the other parameter, if you can remember, I previously said that a new parameter that I found is the spectral density of byproduct. So this parameter also showed that it's actually increasing with every advancing scour step. So these are different types of spectral densities, and all these different types of spectral densities increased for every advancing scour step. So other parameter is actually mode shape, and mode shape also increased for every advancing scour step. So this is also very useful. That means, and you can see that the mode shape is gradually increasing with every advancing scour. So what's shown in the dark lines is before scour, and what's shown in the lighter lines are actually, lighter color shows advancing scour steps. So you can see that when we create scour holes nearby the bridge foundation, so the modal amplitude is gradually increased. So just by looking at these modal amplitude increases, we can say that the bridge has bridge has covered. So in summary, the most important finding is that structural health monitoring can be implemented by just by looking at the vibration-based properties. And also natural frequencies reduced due to scarf. So in the field experiment, I did not see a natural frequency change, but in the laboratory experiment, I saw that for all the models, natural frequencies lowered for every advancing scar step. Other important finding is that mode shapes also increased because of scar, and also model spectral densities increased because of scar. So that means by looking at all these three parameters, if we look at all these three parameters, every type of bridge, we should get the types of bridges I looked at least, we should get some indication of scar by just by looking at the vibration properties. So that's it, guys. If you have any questions, feel free to ask me. Yeah.
Thank you very much, Kasun,
Thank you.
for that very interesting presentation. Yeah, so we'll take questions. If you have questions, kindly unmute and ask your question.
Amila, what did you think?
Hi, it's a nice presentation. I got one question about finding mode shapes. So,
Yes.
in your experiments, how did you measure the mode? Uh, how did you know this is the mode shape, and
Yeah.
how did you measure the mode shape?
Yeah. That's a good question. So mode shape, what we do is that the best way to find mode shapes is to, if we can find out, so find out mode shapes, we have to have accelerometers at different locations. So if you can, remember, so the mode shape you saw that it's quite like at distinct points, right? These distinct points are actually like, you can see that the real mode shape of the bridge will be really curved. It's not like really, uh, uh, it's like not broken here. So all these different points, so you can see there are 4 points here. So I had 4 different accelerometers here. So you have to have different accelerometers at different locations. So each location shows a modal amplitude. And then by plotting the modal amplitudes, you can see what is the mode shape. So to get the modal amplitude for each and every accelerometer, so what we do is that if we have the input excitation as well, so we can develop something called frequency response function. So just by looking at the the at the modal peak, so whenever there is wherever there is the natural frequency, there is a modal peak. So it's like a peak. So at this peak, so frequency response function at this peak indicates the modal amplitude. So that's if we have the input excitations. If we don't have the input excitations, what we do is we assume the input excitation is just broadband. That means like input excitation is like having natural frequencies everywhere. Input excitation having frequencies everywhere. And looking at that, we can say that, and then there's something called frequency domain decomposition. Maybe Paul knows about it. Well, actually, it's a technique used in mathematics a lot, I think. So frequency, whenever you do this technique called frequency domain decomposition, you just decompose a matrix. So matrix into separate components. So one of these matrices provide the modal amplitudes actually.
Okay, thank you very much.
That's right.
Okay. I think there's another question there. What kind of structural defenses are there against cow?
What we usually do is that we use riprap. Riprap is just basically big stones. So we just dump a lot of big stones because scour happens because of erosion, right? So to avoid the erosion, we can drop a lot of big stones, because the big stones do not get washed away because of water. They just stay there and they avoid further erosion. So that's the most common way. And there are more advanced techniques, such as you can have different devices which kind of deflects water and make sure that the water does not get the water does not go there and kind of erode it. And also you can have you can reinforce the riprap. So some people, what they do is that they use concrete with a riprap. So you create kind of a reinforced riprap. That's riprap is the most common technique actually. Any other questions?
Thank you very much. And thanks, Sam, for asking that question. Any more questions? Okay. If there is no more question, please can we give Kasun a round of applause for that wonderful presentation. Yeah, and thank you very much for speaking. And thank you everyone for coming as well. And would say all the best to Kasun on your Viva as well.
Oh, thank you. Thank you.
Yeah.
Thank you very much, everyone, for coming. Thank you.
Thanks.
And thanks for the questions as well.
Thank you.
Good luck.
Thank you.
Thank you.